Hi everyone! The topic of our presentation today is Bad Physics, the Matrix. The presenters are going to be me, Ashley, Brendan, and Haifeng. In our presentation today, we're going to explain two misconceptions found in the movie The Matrix. In the scene where Neo stopped the bullets coming towards him with magnetic field, we found two physics misconceptions. Let's watch the video. So what's wrong in this video? In the video, Neo created a magnetic field around him to stop the bullets coming towards him. This magnetic field would need to be really large in order to stop the bullets coming with momentum mid-air. This means if the bullets are coming with really large velocity, in order to able to counteract the forces, the magnetic field has to create a really large magnetic force. Even if we could create the magnetic field, it would not only affect the bullets, but also affect other magnetic materials in the surrounding. Secondly, the force of the bullet cannot be in the same direction as the velocity, according to Fleming's right-hand rule. Physics concepts required to understand this will be explained next.
Hey guys, let's talk about the physics concept related to the misconception. A magnetic field is a vector field produced by a current, a flow of charged particles, or magnetized material. Force is the push and pull on an object with mass that changes its velocity. Then is the right-hand rule. The pointer finger is in the direction of the charge it's moving. The middle finger is in the direction of the magnetic field. The thumbs points in the direction of magnetic force push on the moving charge. Now let's talk about the Lorentz force equation. The force exerted by the magnetic field on the moving charged particle is described by the Lorentz force equation. Is the force is equal to the charge of the particle multiplied by the vector cross product between the velocity of the particles and the magnetic field. Finally, we can talk about the misconception number one. In the movie, Neo stopped the bullet without changing their direction. So we think the force diagram of the bullet are looking like the image on the left top. There is a force in the directly opposite direction of the velocity vector, but that is not how the magnetic field force acts on the bullets. Looking at the left bottom image, the direction of the velocity is not changing. When they are in the magnetic field, there is a direction of the magnetic field, no matter what direction the magnetic field is. Into the page, out of the page, up or down. It is impossible to have a force to be 180 degrees apart from the velocity vector. Therefore, the bullet cannot be stopped in the air just like in the movie. So they might move in a curved shape.
Now I will introduce the second misconception. In order for Neo to be able to stop the bullets, he must generate a magnetic field with a magnitude high enough to counteract the momentum of the flying bullets. To be able to solve this situation using our physics equations, we first have to make four assumptions. The first assumption is that the mass of a bullet is 0.01 kilograms. Now for the second assumption, we must acknowledge that the velocity of the flying bullet is 300 meters per second. And for the third assumption, the stopping distance of the bullet will be 0.1 meters, and the bullet will be modeled as an electron, which we all know has a charge of negative 1.6 times 10 to the negative 19 coulombs. First off, we have to revisit some topics from Physics 31A, in which the change in momentum, delta P, is equal to the mass of the bullet mb times the velocity of the bullet vb. Now we learned that the force exerted by a magnetic field on a moving charged particle can be described using the Lorentz force. where the force equals the charge of the bullet, QB, times bullet velocity and the magnetic field. We also know that force can be expressed as a rate of change in momentum, which is given as force equals the change in momentum delta P divided by change in time delta T. And now we can combine these two formulas to get charge times velocity and magnetic field equals mass times velocity over the change in time. Now we can isolate B and solve for B, but before we do that, we can use a familiar formula of velocity equals displacement over change in time, which can help us solve the equation using our given values. Since velocity equals displacement over change in time, the manipulation of the formula will make change in time equal displacement divided by velocity, which then we can plug into our formula. After rearranging and plugging in our given values, we see that the magnitude of the magnetic field required to stop the bullet is 1.88 times 10 to the 20 teslas. We did decide to take the absolute value of the magnetic field so we could focus simply on the magnitude, as misconception number 1, which we discussed earlier, showed that the physics in the film completely disobeyed Fleming's right-hand rule. And also to address the cross product, we did have to assume that the angle between the velocity vector and the magnetic field vector was 90 degrees, which gives us sine 90 degrees equals to 1 in order to evaluate the cross product. We knew that applying 0 degrees would make the equation equal to 0, and there was not enough information provided in the film to allow us to calculate a precise angle that can relate the magnetic field vector created by Neo and the velocity vector of the bullet.
So what are our two misconceptions? Our calculated magnetic field is 1.88 into 10 to the power of 20 teslas, which is many magnitudes larger than the magnetic field strength ever encountered in nature or produced artificially. The strongest magnetic field ever produced is 45.22 Tesla in China at the Steady High Magnetic Field facility using a hybrid magnet. This value, when compared to our calculated magnetic field required, is very small. The direction of the bullet is also wrong, as it disobeys the laws of physics and concepts of Fleming's right-hand rule. So, we can conclude that Neo should not have been able to stop the bullets as shown in the film. This is our works cited page, and thank you all so much for listening.